Welcome back, ladies and gentlemen. Today we're going to talk about something that gets me personally very excited, and that is the nature of light. Specifically, we're going to talk about how the nature of light helps us understand light refraction and how light refraction is modeled by Snell's law. The reason I enjoy learning about light so much is that it is immensely complicated topic. There's always something new to learn, and it also helps you understand a lot of the modern technology around you, like wireless communication and how your popcorn pops in your microwave, etc. It helps you understand quite a lot of modern technology. You may remember, or you probably remember a few days ago, I gave you a pre-test in this topic, and I gave you a list of 9 or 10 questions. Most of them are there up on the screen in front of you. What is light? What is a rainbow? And then a few questions about what a rainbow is. But I was most interested in your responses for what is a light and what is a rainbow to see what you knew. And I was actually quite impressed with the quality of responses that I got. Here's what most of you, or if I can kind of consolidate it and summarize what you guys knew about light, you gave me some pretty good high quality answers, and that light is energy, a wave, or electricity. You kind of knew that it had kind of an electrical component, you knew that it was related to energy, and you knew that it had wave-like properties. And your definition, your collective definition for a rainbow was basically dead on, which was a separation of colors of white light. We're going to talk about rainbows a little later because we have to understand refraction first. But I wanted to give you a formal definition of what light is. And here it is. So not only do I have a definition, but I also have a picture. The official definition for light that we're going to use we're just going to call it electromagnetic radiation. And those two words can make you sound really smart, but when you string them together and you ask yourself, what does that really mean? You probably don't have much of a great idea of that because you don't know much about electricity at this point in your life. You don't know much about magnetism at this point in your life. And you don't know much about radiation at this point in your life. But I'm going to fix that just a little bit, help you understand it just a little bit. And the main idea here is that light is made up of two waves that are oscillating in perpendicular axes to each other. So this drawing here is wiggling super fast, and it's propagating through space in this direction. And it has an electric component to it and a magnetic component to it. And that's pretty much exactly like what it sounds like. It's kind of like electricity. I don't want to say it's electricity, but it interacts with electric fields and it interacts with magnetic fields through these two waves. So it has a magnetic component and an electric component. And most importantly, they are synchronized, they are perpendicular to each other, and they're always kind of in this orientation to each other. So in this picture, there are some GIFs out there on the internet that will actually animate this for you, but if you kind of trace the strongest bit of the wave, the most intense part of the wave, we kind of travel through space like this, and it kind of makes a corkscrew action, and that basically looks like this. So as these two waves oscillate in synchronization with each other, they kind of cause this three-dimensional corkscrew or helix kind of rotation through space as it propagates very quickly. So again, these things are wiggling super fast, and they're also propagating from left to right very fast. In fact, you probably know that speed of light is kind of like the ultimate speed limit of the universe, and it actually has a constant speed attached to it of 3.00 times 10 to the 8th. That's 300 million meters per second. And you'll see in this video I've included a little asterisk right there, and that little asterisk right there we're going to talk an awful lot about. So remember that asterisk as we go through this video. The last couple things that I want to talk to you about light is that it's very weird. Sometimes it will reflect like a particle and you can treat it like a Newtonian object, and other times it acts like a wave where it interferes with other, and when I say interfere, it can build on, amplify, or it can degrade or cancel out other electromagnetic radiation. Or it can interact with electric fields or magnetic fields. So it kind of has this dual nature, and it can pretty much interact with anything in any way that it wants. It's a super complicated topic, but basically what you need to know is that it has an electric component and a magnetic component, and it propagates through space. So what I'm going to do on this next slide here is I'm going to draw a simplified version of this because I don't want to look or think about this in three-dimensional space all day long. So I'm going to take this, just this one wave right here. We're going to simplify it to one wave, and I can do that and represent the entire wave like that because all these waves, or this corkscrew, are all synchronized to each other. So I can take this picture and basically just turn it sideways, flatten it out, and I get a relatively simple drawing like that. Now, being that this is a math class, we want to attach some numbers to that. So we'd like to be able to measure some stuff off of there. So one of the features of a wave is that it has a peak. And if we can figure out how far those peaks are apart, we can also measure in time how far apart they are occurring. And that is what frequency is. And frequency is by far the most important characteristic of light in terms of what that particular beam of light or photon of light is. It is the most descriptive characteristic of light that you can give, and it is a count of how many peaks pass by per second. So when we talk about frequency, it's number of wavelengths per second, or basically number of peaks per second. And you're probably already familiar with the word hertz because you hear that a few times in technology, like cordless phones operate at 2.4 gigahertz. A radio station, like say the current 89.3, well, that's actually 89.3 megahertz, which means that the signal that they're broadcasting has a count of 89,300,000 peaks per second. And in the particular example of a radio station, they own that frequency. So they are the only ones that are allowed to broadcast on that frequency. So they have a super fancy, super precise transmitter that will transmit only on that frequency. And the light that they transmit, the radio waves that they transmit, will always be at that frequency. So that's another major idea for the day, is that frequency of light is determined by the source of whatever created. So if something creates a relatively high frequency wave, and we're talking just within visible light here, so if we have high frequency, it's high energy, and if we're talking about the visible spectrum, it will appear bluish to us. If, on the other hand, you produce a low frequency wave, it has low energy and will appear red if we're talking about the visible spectrum. Now, the world doesn't end at blue or purple and red. It goes much farther beyond either side of that. So this next picture here shows the entire spectrum of, well, not the entire spectrum, but most of the spectrum of electromagnetic radiation. So you can see that the visible band, what we're able to see, is just a tiny, tiny sliver, and this might even be an exaggeration of what portion of this entire spectrum we're able to view with our own eyes. But you can see that lower than red, you got infrared, microwaves, radar, radio, etc. And above purple, I'm talking about above in energy, you've got ultraviolet, X-rays, gamma rays, etc. So higher energy, smaller wavelengths in this direction, lower energy, longer wavelengths in this direction. So this is the entire spectrum. This is just a blown up version of the visible light, and here's a little thing that says, hey, increasing energy goes this way, smaller wavelengths go this way, and increasing longer wavelengths go that way. I wanted to show you this as well. This is the intensity of the sunlight that is transmitted from the sun based on color. So you can see that the intensity of red is pretty low, but there's a big wide band of it. And the sun produces a lot of yellow and green and blue light and very little purple light, low intensity, and not a very big thick band of it. And if you combine that with the idea that in terms of human eye sensitivity in detecting color, the human eye is not very good at detecting red, true reds, but there's a lot of red that we can actually see. We're very good at picking up oranges, yellows, and greens, and then again, not so good at bluey greens and blues, and definitely bad at detecting purple. If you combine those two ideas, that the sun does not produce very much violet light and we are very bad at seeing violet light, you can answer one of those rainbow questions, that is, why don't you ever see violet light in a rainbow? And it's just because, one, the sun doesn't produce very much of it, and secondly, humans aren't very good at seeing it. So I want to represent light for you in one more way, and that is using a ladder diagram, because a ladder diagram is going to help us understand refraction. So on the left I have a high frequency blue wave, and on the right I have a low frequency red wave. And I'm going to show you just how I'm going to even simplify these drawings even more by creating a ladder diagram. Basically, I'm going to identify the troughs and draw a vertical line to it, and I'm going to make something that looks like a ladder out of it. And I'm going to do the same thing over here. And you can see that by comparing those two ladder diagrams, you're very quickly able to see that this is a lower frequency wave and this is a higher frequency wave. And pretty much everything, every characteristic of this wave in terms of numbers is maintained. I've got a wavelength right here, and I could count how many wavelengths happen per time. The second thing I want to recap is that idea of the speed of light. And remember I said there was an asterisk there, and we're going to talk about that asterisk right now. And you've all been told that the speed of light is constant, it's the ultimate speed limit of the universe, Einstein is amazing, so on and so forth. But there's a little dirty truth to that we haven't actually told you, and that has to do with that asterisk. And what that asterisk means is the speed of light is only the speed of light in a vacuum or through empty space. In other words, it is possible for the speed of light to change and more or less slow down. If you send light through a medium, something that is transparent or translucent, it will propagate slower through that medium. So the speed of light is not constant, and that has to do with that electric component to the electromagnetic wave. As soon as light starts interacting with matter, that electric component starts basically interacting with other electric components of matter, specifically the electrons. So the light wiggles the electrons wiggle back, and all their waves add together and destructively interfere with each other in such a way that the overall sum of the wave is something that propagates slower through the medium than it would otherwise. So don't think of it as like a pinball. It's more like a sum of waves that basically makes that propagation speed a little bit slower. And the giant caveat to this is that if it's a red beam of light going from one medium to another, it will still remain a red beam of light. In other words, frequency from medium to medium will always be maintained. If you start off with blue, you'll still have blue in the new medium. Frequency is not changed, just the propagation speed is. So if we look at, for instance, a red beam of light about to enter a new medium, and it's got this nice little beat going, bump, 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 bump. It needs to maintain that bump even if it slows down. Okay, so if the propagation speed slows down once it hits this medium, it's got to decrease the wavelength to keep the beat going. Okay, so as this wave goes from one medium going very quickly to something that's slightly slower, it's got to shorten up its wavelength in order to keep the frequency, to keep the beat. And you might look at that and say, sweet, problem solved, no big deal. But there is a problem, and it's right there. And you might say, oh, it's just a little kink, no big deal, we can smooth that out, no biggie. Well, it's a little bit of a biggie, because right here you've got a wave of light, and then on this border you don't know what you have, and then all of a sudden you've got a wave of light again. So you go from having something to not having something to having something. And that's a big deal in reality, because you can't go from having something to not something to something again, because there's some discontinuity there. To exaggerate the issue, it's basically the same idea as this. You've got this gap in this physical idea, and that's just not possible. You can't do that. You can't just skip over time, space, all that fun stuff. So you have to straighten out the curve somehow, and the only way to do that is to bend it. And if you bend it, you straighten out that curve, keep it nice and continuous, and you go along your merry way. And you can see right here, we've got a beam of light that is all of a sudden deflected at some angle. And that is the basis of refraction. So here I want to illustrate the point with a ladder diagram. We have an incoming beam of red light. Once that incoming beam of red light hits the medium, it's going to have a new frequency that has a shorter wavelength, and you can see that it's really difficult to line those up unless we rotate it and knock it together like that. Same thing if we have a blue beam of light, we're going to have to do the same thing, and you'll notice that not the frequency is higher. I shouldn't say the frequency is higher, the wavelength is shorter. The propagation is slower, frequency maintains itself. But again, the red light needs to bend and the blue light needs to bend. And the reason I did a red beam of light next to a blue beam of light is you will see the angle of deflection, the amount that the light bends is much greater on the higher frequency wave. And that's a major concept here today too. Higher frequency will bend more than lower frequency. Now, if you let a mathematician get a hold of this, they're going to have a whole lot of fun with it because, you know, you've got two linear lines, you've got measurable angles, and all of a sudden you've got a drawing that looks like this. You've got medium 1, medium 2, so you have a boundary here. You have an incoming angle of incidence right there and an outgoing angle of refraction right there. The only thing that's tricky about this drawing is that it's always in reference to the normal line, because we can't always assume that this surface is going to be flat. It could be curved or irregular or whatever. The normal line will always be there. And remember, a normal line is something that's perpendicular to a surface in all directions. So as you can imagine, there are some people out there that decided that that was something that they wanted to talk about because it'll help explain a whole lot of things about light. And basically they developed this law. They derived this law. It's called Snell's law after the dude who invented it, or developed it anyways. And you can see that it's a trig function of theta 1, so it's related to the sine of theta 2 divided by the sine of theta 1, and that's equal to n1 over n2. And that's the part that's new for you, and that is basically just a property of the material that is being material on either side of the boundary. So this n1 value is called the refractive index for this substance, whatever it is, and it basically is a number that tells you how much, to what severity, light will bend when entering that medium. So here's your definitions for all the variables in here. Theta 1 is the angle of incidence, theta 2 is the angle of refraction. This is the refractive index for this medium. So if that's air, you go into this giant table and you look up the refractive index for air. If this is water, you go and look up the refractive index for water. And there are giant dictionaries of these things for every known substance that light can transmit through. So I'm not going to give you the big thick dictionary. I'm going to give you an abbreviated version of that, and you can see that we've got 5 different substances that we give the refractive index for. And notice that I did it for both red and blue light, and you can tell 2 things. One is that as you go from less dense stuff to more dense stuff, in general, light bends more in more dense material than in less dense material. And the second thing you can see by looking at this table is that blue light always bends more than red light. A bigger n value here indicates that it bends more. So let's do a problem, finally. Here's a math problem, here's the math part. We have an angle of incidence going from air to glass at a 45-degree angle to the normal. What I'd like you to do is I'd like you to predict what will happen after that white light beam gets separated into a red and a blue beam, and just try to sketch a general drawing of what you think might happen coming out the other end. If you do that, you've got a red beam that'll pop out, and you've got a blue beam that will bend a little bit more. So there's a little bit of deflection on the red beam, and there's a little bit more deflection on the blue beam. And that means that we're actually going to have 2 theta 2s, one for red, one for blue, which really means that we have 2 problems. We have a red problem and a blue problem. And we're going to use Snell's law to do that. So the other thing in Snell's law, we have our incoming angle. We want to find our outgoing angle, so the other thing we need is the refractive index for blue and red for each material, air and glass. So we're going to take a look at these 2 rows in the table that I gave you. So we're going to use Snell's law, so we're going to set up the formula for red. We'll go red first, then we'll do blue. No particular reason why. You could start with blue, no big deal. And we're going to plug in everything that we know. So we know that the angle of incidence is 45 degrees. We need the n value for air and red light, so we go over to our table and find that. We need the n value for glass and red light, which is that number right there, and we plug it all in. And from there, it's a cross multiplication problem. So cross multiply, I evaluated the sine of 45 degrees. That's been rounded or truncated. Then I'm going to divide by 1.609, and then to undo the trig function, I'm going to take an inverse trig function of both sides, like that, and I'm going to get 26.07 degrees. And from there on, so what that means is that 26.07 degrees is measured from the normal to the red beam right there. So that will be 26.07. So we know that our blue degree measurement, our blue theta 2, should be less than that because it's going to be tighter to the normal. And to do the blue line, we set it up exactly the same. We use Snell's law. We plug in all the values, this time for blue light, so we've chosen 1.0 and 1.643. Cross multiply, divide, take a inverse trig function, and we've got that degree measurement. So we can actually physically draw on whatever we're drawing on that is a tighter angle to the normal, and all of a sudden we have this separation of colors. So we have a red beam and a blue beam going through, and every color in between, the oranges, the yellows, the greens, will appear between the red and the blue in that order. And right here, if that were to strike upon some sort of flat surface, say like right there, if that were just like a white wall right there, that's where your rainbow would be. I'll see you in class and we'll do a couple more of these problems.